To start off with, as Steve said, I've worked in cybersecurity really for almost 40 years. And an interesting question that continues to come up is, well, what is security? And what is cybersecurity? And I leave out the cyber here, but if we talk about a system being secure, what do we really mean by that? Or if we talk about security features, what is it we really mean? Because those are the things that we would like to be able to support. So we'll start with an intuitive definition. And that is that a system is secure if it's protected against all forms of threat. Because threats are things that can compromise our security, so we want to protect against them all. Let's give that some thought and see what some of the implications of that might be. So can we build a system that, or maintain a system that keeps out random hackers? I would say generally yes. There are a lot of people who can do this. Requires some constant vigilance, but we can do this. Can we build a system that's resistant to any kind of malware? Probably. We have to worry about users who click on links and install untested kinds of media, but we can generally protect against these kind of problems, and we have many systems that are operational that are resistant to any kind of malware. How about nation-state hackers? Well, here we begin to run into a problem. There are some very sophisticated groups out there, some nation-state, some very large organized crime syndicates, very clever, very difficult for at least individuals and for many organizations to defend against. So now we're getting into some difficult territory. But remember, we want to protect against all threats. So how about a UFO invasion? I don't think we are there. That's something that is probably going to be beyond our understanding. And of course, this is assuming that such a thing exists, but being able to protect against it is an issue. How about an extinction event meteor impact? I would say definitely not. We can't even protect ourselves against that, let alone our computer systems and the data on them. So that's a real problem. Now, if we were to think about this some and willing to invest enough time, energy, and money, as well as employing the technology, we could maybe set up colonies on Mars, for instance, and give them backup copies of all our systems. And would that be protecting our systems against all kinds of threat? Well, no, because I can come back and say the eventual death of the sun will mean the end of the inner planets. And that includes Mars. So that's not going to work, even if we were able to establish a Mars colony anytime soon. Well, I can imagine that your next step is thinking about, well, all right, how about the outer planets, maybe some of the moons of Saturn, other galaxies, where could we go? And the answer is, well, physicists talk about the heat death of the universe, and as of yet, we have no idea how we would protect against that. Admittedly, that's billions and billions of years from now, and so maybe our data won't survive that long. But from the standpoint of using that definition of security, it just isn't a workable definition. And it's not that helpful because no matter how we approach it, in the general sense, we can never achieve it because we can't anticipate every kind of threat. We don't have the technology or the resources to protect against every kind of threat. And really, this exposes something underlying what we do in cybersecurity, which is not well understood by everyone in the field, is that security is at its heart an economics issue more than it is an engineering task. It's deciding how much to spend and where to spend it to minimize the risk to an acceptable level. And that's simply because absolute security is unattainable. It really depends on the context and the resources and what it is we're trying to protect. I don't know how many of you are familiar with the name Robert Courtney or Bob Courtney, but he was one of the pioneers in the area of information security. He was the first chief security engineer at IBM back in the 1970s. And he articulated 3 laws of security that I think deserve greater recognition because they really are spot on. And they relate to a lot that we have to talk about in terms of the human component of security. And I list them here. So you can see the first, nothing useful can be said about the security of a mechanism except in the context of a specific application and environment. And this gets back to what I was saying about being able to anticipate the threats, whether they're a meteor or heat death of the universe. If those aren't part of the environment, then we don't have to worry about them as threats. Second, never spend more mitigating a risk than tolerating it will cost you. And that's the economic aspect of security. And then the third, which is often overlooked by people who are technically focused, is there are management solutions to technical problems, but no technical solutions to management problems. And this is key, because people are very often the cause of some of our difficulties, and being able to manage people is part of the solution that we want to have in security. So another attempt that we can make is, let's maybe look at the issue of system design, and can we do a better job there? And this has been looked at before. Back in the 70s and 80s is when it started. And the idea of looking at a system state. And we basically define the state of a computer system at a moment in time as either an okay or safe state or not. And this is in the context of a policy, such as the well-known Bell and LaPadula policy, or BIBA, or some other kind of policy model that allows us to define these states and something about transitions. Because as a system executes, it changes its state. And the allowed states or okay states are the ones that we want to transition into. So any valid operation results in the system also going into an okay state according to the policy model that's in use. But this implies that there are bad states, states we don't want to enter into. And bad is a qualitative kind of judgment, but it's unallowed states. Maybe they are a violation of security or privacy or something else, but we don't want those to occur. We don't want to enter those bad states, and we especially don't want to remain in them. Because here we have the notion of allowed states are effectively a match to the concept of system specification in software engineering. We specify what are the allowable states. And the execution of a state not in the specification is a fault that can result in a failure. And a failure in a protected system is a security failure. And for those of you who've been doing this long enough or looked into the research in this area, yes, security was one of the prime drivers in the initial development of software engineering, the other being cost, to try to get systems that behaved correctly and didn't overrun design. But security was a big driver here, the idea of specifying what is correct and what happens if we do something that isn't correct. Now, if we have these defined states and these bad states, we also have undefined states. And our own experience is that we have these states, we haven't anticipated them, we haven't specified them, but they're not necessarily bad states. They simply aren't described. Entering one of these is an error as well, and can be a fault, but they're not necessarily a long-standing security problem. They may not be a complete failure, especially if we're able to re-enter one of the good states as in a next step. Because they may lead back to these okay states, but they're undefined. So we don't know. We haven't thought about them. We haven't defined what they are. We don't know what the consequences are. So this is the model that was really developed, and a lot of work on software engineering was around this. But in truth, as we develop more experience with software, we understand it probably looks more like this, that the set of undefined states is much, much larger than the set of defined states that are either good or bad. And that makes things considerably more difficult. Most software today operates in this undefined state space because we've never defined its proper behavior. And that's just a consequence of the way we build software. Because to build those formal specifications is time-consuming and expensive, and it also requires expertise that we don't generally have in the community. There is such a demand for people to build software that we have many people who are not trained or even not capable of understanding how to formally specify software. And so this is largely fallen by the wayside. What we end up having are very general requirements and no detailed specifications. So we don't even have a full set of requirements for most software. For the functional requirements aren't even fully specified, let alone the non-functional. And issues such as privacy and security are really non-functional requirements. If we don't have those requirements, and certainly no specifications, we can't really define correct either. So one of my favorite quotes relating to this is from back in 1985, and this is where it appeared in print. Earl Bogart was allegedly the one who actually stated this, is that a program that has not been specified cannot be incorrect, it can only be surprising. And so most of the software that we're using today, by far the majority of software we're using today, when we say that it has, that it's incorrect or that it's buggy or it has a security problem, that's not really correct. What's happening is it's surprising. It's not that something went wrong, it's just it surprised us with its behavior because we never really specified it in the first place. Another consequence of this is we just overbuild and we continue to tack things on. Software continues to add on features and additions, some of which is dead code with interactions that we don't understand because it wasn't really designed in the first place. And as a result, we get some incredibly complex software. We look at industry practice and we find that many companies are willing to hire people who have no real training, buy a course for a weekend crash course or a book on programming. And if it's not C++, it's PHP or Swift or Go or whatever the current language is that they're using. And as long as they can write a program that compiles, sometimes they're hired. For those of you who've been around long enough that you remember the movie Jurassic Park, and I'm finding that many of my students now in classes haven't seen this because it's too old, but you may recall that the billionaire spared no expense to build the park and all the amusements and recreate all of the dinosaurs in the park, bought an island, and basically hired one IT guy. And of course, disaster came about as a result. But that's precisely how the industry operates, is IT and all of what's involved in running it and designing it is given a very minimal amount of attention. I have this next picture that I've used a lot because I love it, but I would say that this is a metaphor for our current software, that we started off with some very simple needs, but over time we've just continued to patch it and add things on to eventually where we get to the point where we have these monstrosities that never really get rebuilt. All we do is have the next release, the next version. that has patches and additions and new features, because it's very difficult to take old parts out and do so in a way that doesn't break something else. This is a consequence of a very bad feedback loop that is driven by some economic and user expectations. Right? So that relates to this workshop, this symposium. Is again, the human element is involved here. And part of it is this expectation with sunk cost. So what happens on this loop, as we look at this loop, is somewhere in this space down here, our computers have gotten slow. Everything we're running on it use up all the memory. We're utilizing the processor because we have so many concurrent processes running, things in the background. We've got so much going on. And so we reach a point, either in our personal computing or in our business computing, where we have to get a more advanced computing system. And we go out and we get a more complex, faster system with more memory and more peripherals so that we can run all our software. Now note, what we're getting is not a new system in the sense of new from the beginning. What we're doing is we're getting a newer system that runs all our same software. And everything is great for a while. It runs really quickly and fast, and we're able to load up new applications, and then the vendors do new releases and they add new features, and we take advantage of those, and there's more background tasks, and the software gets more and more complex until eventually we're back down here where the hardware isn't able to support all the software. But at any step in this cycle, if you ask someone about, well, why don't you throw it all out and start over from the beginning? And you'll get a look of just horror from people because they're familiar with the software. They've been trained on the software. It interoperates with everything else they're doing. The software runs on the hardware they have, and they put so much expense into it, they can't afford to get rid of it. And so what happens is the software gets more complex and the hardware gets more complex. And as a result, we continually get more and more complex as a stack to the point where we no longer really understand all of what's running. I would say even 10 years ago, we had people who, with effort, could understand everything that was happening from the hardware up to the user interface. That's no longer possible for the typical system because we have put so many layers of virtualization and containers and multiple processors and shared memory and buses and distributed computing and cloud and different layers of abstraction of software and data. It's no longer possible for one person to be able to keep all of that in mind. So where do we go? Well, where we go is basically an issue of trust. And this is not something that is verifiable in a formal way. This is something that we have to build. And I've given here some definitions, and I won't go through all of them, of trust. These are from various dictionaries. But they all go to the idea of belief. They all go to the idea of confidence. And that is of human beings being able to be confident of or believe in a system meeting its design constraints. Again, this is if we have captured the requirements and specifications. So there's an assumption here that we have at least some set of principles that we'd like to believe in that the system is going to follow. And this is really the chain of thought that occurred in the 1980s and 1990s for the people who were really devoted to looking at security. And it leads us to here, to the idea that cybersecurity is the science and practice of protecting information and components from misuse. Now, misuse is relative and protecting is relative, but this is effectively where we have gotten to from using this concept of trust is looking at this entire stack and protecting against things that we are going to label as misuse. But to be able to have the trust rather than the security, we actually are going to follow the path of assurance. And so that's where we increase our confidence in the system rather than trying to ensure the security of the system. What we want to do instead is put in those practices and procedures and technologies that allow us to have a greater confidence and a greater good feeling about how the system is going to behave. And this kind of punts on the whole idea of what security is. So, we can't have perfect security, but we can increase the trust. And so that was the conclusion that basically we came to as a field in the late 90s, early 2000s. But that didn't solve things. And again, we're back into users and user perceptions and values, which we can't get away from when we're talking about security. The first is the idea of trust alignment. If we're going to trust a system, how do we align different views of trust? Because trust is relative. Trust is to a set of values. So I have my goals and values about what I want a system to do. My employer has a different set of goals and values. And then our society or our government has yet another set of values. What we want is to align those in some way so that when the system operates, all of those values are upheld. But the typical systems in operation today don't have that alignment. So whose trust do we support? And you might ask, what's an example of where these don't align? Well, a fairly simple one is the current tension between law enforcement and individual users and companies over privacy in relation to encryption. So we have governments and some employers that don't want values that can be encrypted that they can't see, and yet we have users who are concerned with their privacy, or companies that are concerned with their trade secrets that do want to have strong privacy, and that's not in alignment. This is at least as much a human problem as it is a system problem. And we haven't done a very good job of articulating those human values in a way that we can translate into system design specifications, or in showing limitations of systems that we can build relating back to the human systems that govern them. So this is an area of great importance in the human-computer interface area of just translating policy and trust. Another is compounded trust. I mean, what are the limits of trust? We don't really completely understand that. There's the issue of supply chain. Do we trust our suppliers? Do we trust the suppliers our suppliers trust? How far back do we go in building that trust, and what level of assurance can we get? Because we don't really completely understand trust, we don't know how to decompose it. We don't know how to tune it. And I would say even more fundamental to this whole question of defining trust is that of measuring it. And that goes to what Lord Kelvin wrote, and I suspect many of you are familiar with this, when he was saying what you can measure, what you were speaking about, and express it in numbers, you know something about it. But when you cannot measure it, when you cannot express it in numbers, your knowledge is a meager and unsatisfactory kind. It may be the beginning of knowledge, but you have scarcely in your thoughts advanced to the stage of science. And that really is key when we look at the definition of science or of engineering, where we're going to build repeatably and be able to compare things that we build. We need measures. When we talk about any kind of science or engineering, we have units of measure. we have items to measure with. And these are some of the simplest in terms of physical measures of weight or distance or time. But what do we measure if we're talking about security, cybersecurity, privacy? What are the things that we measure? That gets to a basic problem of we don't even know what security is, which gets back to what I was saying in the beginning. Now, we have this traditional view of security having these three properties, and this is the way we describe it generally to introductory students or to people outside the field. But this is a really rotten definition in a lot of ways. And I can tell you, there are a couple conflicting stories where it came from, but one is that it was developed as part of a sales presentation. Bob, who I mentioned earlier, I was doing an IBM sales engineer presentation, and management wanted him to convey to the people involved that they had to consider security as part of their sales engineering job. And he came up with the idea of this triad, not because it was an ideal representation, but because the initials CIA were catchy and would probably get the sales engineers to remember them. The idea of they were supporting CIA, remember this is back in the 70s, was a really amusing idea. And it stuck. It stuck so well that we're stuck with it today. But it's not a good model. Those measures aren't well defined. They're not orthogonal because they overlap each other. If you change one, it can actually change one of the others. There's no natural measure for any of them. We don't know what they are really in terms of being able to measure them in a repeatable way. I have gone through some papers and textbooks and replaced integrity, availability, and confidentiality with rock, paper, scissors, and the discussion basically makes about as much sense. You can try it yourself. It doesn't really describe fundamental features that we can measure or that we can easily articulate in any kind of design. There have been attempts to improve this, and Don Parker developed his HEXAD model, which I like better, but it has the same problems because it includes the original three. They're not orthogonal. They're not. They don't have natural units of measure, and so on. There are some issues here about utility, and that goes a little bit to an important aspect of correctness and user accessibility, but it's still woefully short of a good model. So what properties do we need? What are fundamental properties of security? And I think that's an open question. I would say correctness is part of it, that we want systems to behave exactly as we define and nothing more. So an issue of correctness and safety is that the system does what we specify it does. But security needs to go that extra step and say, and do nothing else. And that's a difficult thing to be able to design in and measure. So even correctness as a concept may not be quite right. But if we don't have correctness, we can't say much about anything else. And where are we going to start? And I would say, well, we need to think about composability. And if we're going to base this on trust, whatever definition we use for that, we need to start with issues, for instance, simplicity. Because we know as systems get more complex, they become more prone to problems and security flaws. Specificity. We know that generality leads to problems. We need to have limited interactivity. And this has been known for a long time and is one of the reasons object-oriented programming was very popular for a while and still is, in that we could limit the interfaces and access to variables. But a lot of this also has to do with reducing the information asymmetry. as we think about these issues about simplicity and specificity, we have this information asymmetry between the producers and sellers of our systems and the buyers and users. And this is a human economic problem rather than a technical problem. But in part, it's because we don't have metrics. So there's not a way for someone designing a system to specify these values in a way that the buyer can do comparisons or can specify minimums. So we're a long way off from having good definitions and metrics to even be able to progress towards a more secure environment. I'll outline some other features. As I said, this is not fully defined. We want non-subvertible parameterized access controls. We want intuitive interfaces. And so this is right in the wheelhouse here of this, to use a metaphor, it's right in the area of this group. If people don't know how to use a system correctly, if they don't know what the indicators and warnings are, if they don't know what the settings mean, the system isn't usable as a secure system or as a trustworthy system. We need safe and resilient failure modes, again, that are understood by users. We need non-subvertible identification and tagging of data and items that are in use. We have no idea how to do that. We import data from all over. We don't know its provenance, and that leads to all kinds of problems with stale and incorrect data. We need standardized hardened functions instead of encouraging people to roll their own. We need non-subvertible auditing. So go back and look what the problems are. I can't give you an exact list of all the problems. This is a research agenda. And I know this is something that many of you have been working on yourselves, is to try to define some of these things, or at least pursue elements of it. And we need to do more of that. But I would argue that we need to step back as a field and try to come to some agreement as to what are basic properties and how to measure them. We should be able to have well-defined properties that we agree every system should have. And by well-defined, that means we know how to build them and measure them. We know how they're achievable in context, at least, that they're limited and measurable. And those measures should be composable so that if we put things together, we can say something about the resulting system having properties based on the property measurements of the components. Let me give you some takeaways from this, though, some derivations to think about that relate to the humans in the process. And I mentioned Bob Courtney's 3 laws earlier. The illustration on the right is a colloquially known as a Swiss Army knife. No one in the Swiss Army has one of these, to my knowledge, but the Wenger company that makes these has this one for sale, at least on US Amazon and other outlets. If you look at this monstrosity, which runs in the many hundreds of US dollars, it basically has one of almost everything as a tool that you can think of, including some you wouldn't think of. Now, if you look at that and you postulate that all the tools are there, or you could add another one, you could use this to build a house or construct an automobile. It has all the tools, or at least the majority of them, and we might augment it with a few extra fold-outs to do the things we would need to do. So imagine building a house or even a shed with one of these. You could do it. It's got a saw, it's got screwdrivers, you can use it as a hammer, pry bar, it's got all those things. It's got a ruler. The problem is, it would take you a very long time. The result probably wouldn't look very good. You would bruise your knuckles, at least, badly in using it in construction. And it would be difficult to coordinate the work with others. But this is precisely what we do in building systems. We have these one-size-fits-all languages and interfaces. Right now, we build everything with an SQL database. We use a web browser as an interface, and we build in a small number of languages. We do not have a varied toolkit of tools that are really well designed for tasks that need to be done. Instead, because it's cheaper, we use the same tool for everything. But it's not the best tool. I could go on about this for a while with specifics, but some of you are more expert in the context of user productivity and interface. So think about this a little bit about why is it that we've gotten to the point where cost dominates, speed dominates, to the point of using appropriate technology that we know how to use. And this applies in a number of areas. All the things about interfaces basically go down into what we can fit on a cell phone or a web browser. Everything that we know about operating systems. How many operating systems have we had that have been created in the last decade or 2 decades? Why is everything IoT built on top of Android or Linux with a web SSL interface? That's simply bad design, bad thinking. Part of the problem is we don't stress quality first. We stress first to market, we stress cost. We don't stress quality. And in part, it's because we don't have good measures of quality. We don't have metrics that we can apply to show that something was really constructed with quality in mind, with design first. We basically have people who sit down and start coding before they've even thought through all of the design. Of course, the result of that too is if you don't know what you're building, you're stuck with what you build. And it may be okay while you're building it, but then in operation, there may be some catastrophic results. Does that sound familiar? Some of the software that we've used, some of the software that we've had that's broken, because the people who built it didn't understand the domain of application and built it because it was convenient for them rather than actually fitting into the environment. And then when it comes to security and privacy, we add it on afterwards. We don't really design it in, we don't think about it from the beginning. And as a result, going back to the, if it wasn't specified, it can't be wrong, it's only surprising, we're surprised when the security or the privacy are circumvented. So the result of all this is, I'd like to say, we are the ones who have to define what security is. We are going to have to define quality. We are going to have to take the user experience and the user component into account with what we do. Part of this means that as we continue to do research on problems that we identify, we are failing to look at the overall context, and that's a problem. If we don't look at the overall context, if we don't think what are the fundamental properties that we are building for, what are the fundamental aspects of that human-computer interaction, of that economic aspect of using computers, we will continue to solve point problems and develop patches on systems that are fundamentally unsound. And we're going to continue to do it in a way that doesn't support measurement so that people can look at it and say, oh, that's the wrong direction, because they won't have any of those metrics. Instead, it will look like progress, but all we're doing is adding to the complexity, adding to the mass of broken or potentially misinteracting components, and we're getting farther away from where we really need to be, which is being able to have trustable, assurable systems. So keep up the good work, but think about that bigger picture. And with that, thank you for listening to me, and I'll be happy to entertain some questions.
I think it would be very appropriate for us to unmute all of our microphones and give an actual round of applause to Spaff as our keynote speaker. Thank you very much indeed.
Thank you all.